So hey guys, so it's our great pleasure to have Sven Lilge to give a talk today. And Sven Lilge received bachelor and master of science degree in electrical engineering and information technology from Leibniz University Hannover in Germany. And from 2016 to 2019, he worked as a research assistant in a lab for Continuum robotics at Leibniz University Hannover. He is currently a PhD candidate with the Department of Computer Science and research assistant with the Continuum robotics laboratory at University of Toronto. His research is primarily concerned with continuum robotics for focusing on design, modeling, control, and state estimation. So let's welcome Sven to give a talk today, and the floor is yours.
Excellent. Yeah, thanks for having me, and thanks for the great introduction. Can you all see my slides?
Yeah.
Okay, perfect. All right, yeah. Hey everyone, I'm Sven, and today I want to talk about some of my recent work, which is concerned with the state estimation of continuum robots, and particularly focusing on a method that uses Gaussian process regression. So before we get into the method itself, I just want to briefly introduce continuum robots to the audience. So as we all know, the most well-known and most commonly used robot is this serial link robot. And these robots are usually kind of modeled after our human arms. So they have these rigid links and discrete joints leading to this structure. So yeah, the relative structure is like quite rigid and stiff or strong, and has like very high accuracy and precision, and that allows us to automate a lot of different tasks in industry. So here we can, for example, see automotive industry where the assembly of a car is automated. Yeah, the resulting structure of these robots is like very efficient, I guess, for this type of application, but they are rather stiff and rigid, and the structure can also be quite bulky because of all the joints that I have within. So one of the questions you could ask yourself is, oh, can we actually come up with like a different approach to design robots and a different structure that might enable completely new application areas that rigid link robots can fulfill? So one idea is to not look at us humans and develop robots that look like our arms. We can look into the animal kingdom, and look at elephant trunks or tongues of animals or worms, and ask the question, can we design robots that have no joints within the structure, and what would these robots look like, and what would be the applications that they can enable? And that's exactly what continuum robots try to do. So you can see in this video one example continuum robot. Continuum robots usually consist of a very compliant and flexible material. You can see here in this video already, this material is very soft. You can easily just bend it away, bend it with your hand. And this compliant and flexible material allows the robot to move into these complex and highly nonlinear shapes in 3D space. So I can adhere to a large variety of shapes. And one main characteristic of these robots is that I don't have any joints within my structure itself, but all the actuation is actually outside of this robot. We also talk about extrinsic actuation. So in this specific example, I have a couple tendons that are rotated here along this flexible structure, which we also call backbone. And then all my actuators and motors are outside of the robots here, and they are pulling these tendons, leading to an actuation of this robot in bending. And since I don't have any joints in my structure, that allows me to build these robots actually at very small sizes and form factors, and I can easily miniaturize them. So just to summarize, the main advantages of these robots are that they can adhere to these nonlinear shapes. They have this inherent compliance, which makes them somewhat safe to work with. And they have potentially very small sizes in terms of the diameter of the robot. So looking at these properties of continuum robots, they are very attractive for a couple of application areas. And these application areas are mostly scenarios that have very limited access, some challenging to reach areas, or just like places that feature tortuous paths to reach them and still require manipulation. So some examples are shown here. For instance, in an industrial setting, I could think about continuum robots entering highly constrained mechanism to like do some inspection and repair. So here we can see one example. It's an aircraft turbine. A continuum robot could potentially enter this turbine through a borescope hole and then navigate around the blades and inspect it for damages and potentially even repair it. Another example is shown here on the right, where I can inspect the motor of like a car, for example, without disassembling it. And one other promising area is often stated as minimal invasive surgery, where I want to reach places deep within the human body by only making very small incisions, allowing the robot to enter the human body, or even enter the human body through natural orifices and then navigate around the anatomy of the body along these like nonlinear shapes. So these are like some application areas that might not be possible with rigid link robots, but where continuum robots could be used to enable robots in these specific scenarios. So if we look at continuum robots, we often see robots that adhere to these like highly nonlinear and complex shapes. So one question is, how can we actually accurately describe the shape mathematically and kind of like capture the behavior of the robot in terms of its deformation? So it's a lot more difficult to find a nice kinematic representation for continuum robots than it is for rigid link robots. The kinematic structure of rigid link robots, it's pretty straightforwardly defined. I have my rigid links and my discrete joints, and I can use simple geometric relations to describe them. But for continuum robots, I have this continuous shape and center line. So it's not necessarily as easy to find a good representation of this robot. So I just want to talk about some different options, how I can describe the shape of a continuum robot. So in the literature, there are like a couple of so-called kinematic representations that have been proposed. And on this slide, I just show like three of the most common ones. So the left one here is probably the most general kinematic representation that you can have for a continuum robot, and it's called the variable curvature representation. So the idea is that I describe my center line of my robot along its length. So I parameterize the center line of a continuum robot along the arc length S, going from 0 length to the whole length L. And then I can, for every point along the center line, assign a orientation and position for my center line. So that allows me to basically model any 3D curve in space by just defining for every point S continuously a orientation and position. So this representation can be quite accurate, honestly, and I can like capture any curve in 3D space theoretically. Then there have been proposed some other kinematic representations that kind of try to discretize the continuum robot into kind of like a finite element thing. I have like multiple, I use like simpler structures to approximate the shape of the continuum robot. So one proposed idea is to use constant curvature arcs. So every constant curvature arc is a part of a circle with like a constant curvature kappa. And then I can use multiple of these constant curvature arcs and put them together to represent or approximate the shape of my continuum robot. And one other idea is to approximate this smooth shape of a continuum robot by rigid links and discrete joints. And then I can kind of treat it like a serial arm rigid link robot kinematically. So options B and C, they're quite attractive because they're relatively intuitive geometrically, and they're very efficient to do math with because they're like lead to very like quite simple mathematical expressions. But one big disadvantage is that the accuracy of this representation is actually very limited, because not every continuum robot can be described by a series of just constant curvatures or even a series of rigid links and discrete joints. So I always have some inaccuracies based on this representation. And that's why variable curvature is probably the most used one in terms of the most used one, just because it's like the most general in terms of representing different curves in 3D space. So the next couple of slides, I just want to kind of go into the math of this variable curvature kinematic framework, because it will be important later when we talk about state estimation yeah. So the variable curvature kinematics can be kind of explained using the sketch here on the left. So we see the center line of a continuum robot that is parameterized by its arc length s. So the center line goes from S0 to the whole to the overall length as capital S. And then for every point along this arc length S, I can define a body frame, and then I can find a transformation between my body frame of the robot and some inertial static frame or like world frame. So in this case, we express transformation matrices going from our body frame B to the world frame I. And I can do this for like every continuous point along the center line. And I can use rod kinematics to describe how this pose changes as I go along the center line of my robot. And I do this with differential equations. So this equation describes the change of my pose as I go along S. And this differential equation depends on a new variable, which is epsilon. And epsilon is composed, epsilon are the strain variables of my continuum robot, and they are composed of a rotational part and a translational part. And strain variables are nothing else than just telling me what the local deformation of my continuum robot is at a specific arc length S. So my translational strain variables tell me how much the continuum robot or the material of the continuum robot is undergoing shear and elongation deformations, whereas the rotational part of my strain is telling me how much the material bends and twists in one specific point along this arc length S. And they basically describe the change of my pose as I go along my arc length S. So you can kind of think about them as velocities along S and telling me how fast my pose changes as I go along S. And this analogy to velocity, we will actually pick this up later again, but like maybe keep this in mind to understand what's going on here. So these are my rod kinematics. So that's actually everything already for like in terms of a kinematic representation of my continuum robot. And if I have expressions for my strain variables, I can integrate this differential equation here to recover the shape in 3D space. Now we're dealing with continuum robots, so kinematics alone are often not enough to like fully depict them because they consist of this compliant and flexible material. I actually need to model their mechanics to have like a full picture of what's going on with continuum robots. So I just want to spend one slide going over some material mechanics for continuum robots to develop a full kind of like model for them. And in terms of material mechanics, there are different kind of like mechanics frameworks that I can apply to continuum robots, but I want to specifically focus on Gauss-rod theory. And Gauss-rod theory is basically elasticity theory for slender rods in 3D space. So it's exactly what we want as we're modeling our continuum robot as this continuous one-dimensional line or rod in 3D space. So in terms of mechanics, I will just introduce two new variables to begin with. So one, we have some external forces F of S expressed here in blue. It's usually some distributed forces that are acting on my continuum robot or like on the center line of this continuum robot. And they are thus leading to the deformations of this robot. So generally, these forces are either forces from like contacts with the environment, or they can also be forces that come from the actuation principle that I employ in my continuum robot. So if you like think back of the initial video that we saw, we had tendons routed through the robot. So pulling these tendons would apply forces distributed along the body of the continuum robot, leading to these deformations. So that's essentially what this F of S is. And then I also have some internal material stress, which is denoted here with sigma of S. And now if we consider the mechanics in the static case, we know that our continuum robot has to be in a static equilibrium. So what I can then do is I can enforce kind of equilibrium equations, which put the internal stress in an equilibrium with my external applied forces. The form of this equation is not necessarily important now. It's just important to understand that this enforces the equilibrium between my internal stress and my externally applied forces. And then lastly, I have like one more equation for my mechanics, which is the constitutive law, which essentially relates my strain, so my local deformations in terms of bending, twisting, shear, and elongation, with this internal stress. So it's kind of like this. In this case, this is a linear relationship that we assume for my constitutive law, where the deformations can be mapped via a stiffness matrix to my internal stress. So this linear constitutive law, you can think about it as like a Hooke's law for like a spring. The more I like pull my spring, the more I like increase the strain kind of, and then with the stiffness coefficient, I increase the force that the spring is kind of like trying to pull back together. And it's like nothing else, like it's basically the same, just for like a 6D case in this case. So now we have both our kinematics and our mechanics, and I can use both parts to derive some modeling equations essentially for my continuum robot to describe its shape. So just to summarize, we have the state that we want to describe of this continuum robot with respect to its arc length S. So we have both the pose along S and my strain variables along S, and we summarize these two metrics into the robot state, and I will just call this X of S in the following. And then I have a set of ordinary differential equations to describe the state or the derivative of the state with respect to my arc length. So the first equation are just the rod kinematics, and then the second equations, I use the equations from my mechanics and just like reformulate them to find a expression for the derivative of my strain. So this is just like using the equations from the slide before and bringing them into this new form. So now I have ordinary differential equations for both of my state variables that describe the state with respect to my arc length. And then usually I also have some boundary conditions for these differential equations. So often I know the initial pose of my robot. So in this case, we can assume, for example, identity, because I generally know how I assemble the continuum robot with respect to some word frame. So I do know the initial transformation of the root of my continuum robot. And then I often have some boundary conditions for the strain of my continuum robot at its endpoint that resides from like a specific loading scenario that I assume to know. And now if I like consider these boundary conditions and I consider these ordinary differential equations, can essentially solve the system of differential equations to recover the full state and shape of my continuum robot with respect to arc length S. One important thing to note here, we have in our derivative of our strain variables, we have this variable f again, and this is essentially, as I said before, forces that result from actuation or forces that are just resulting from contacts with the environment of our robot. So when we talk about conventional kind of like open loop continuum robot modeling, we can look at these equations, and what models in continuum robots try to do is they try to find like an accurate expression for this term f of s. So they try to find an accurate expression of how can my actuation be expressed as a force acting on my body. And additionally, they usually also need to know the knowledge about external forces to like solve for the shape of the robot kind of like accurately. So these are already like limiting factors. And especially if I try to find good expressions about how my actuation results to distributed forces on the body, like often there are some assumptions that are made, like simplified assumptions to lead to equations that are actually solvable in real time. One other problem is also that if I like model my robot, I often just assume some material parameters or other parameters in my model that might not be accurate. And all of these reasons often lead to the case that I have like some prediction of my continuum robot from like a forward kinematics model XC, but my real state of the robot is actually quite different, like XC star, for example, here, where I have like this remaining modeling errors or inaccuracies denoted here as delta X. It's because it's like very hard to like model continuum robots accurately due to all the reasons mentioned. So that's kind of where like sensing and state estimation comes in. So the idea now is to actually have additional sensors on my continuum robot body and obtain sensor readings and information about the robot state and shape, and then use this sensor information to compensate for any of those modeling errors that I have in my structure. And this idea sounds very good and promising, but some challenges are is how can I fuse my modeling knowledge with these sensor measurements? And how can I do this actually in an efficient way? So I can formulate and solve this problem very efficiently so that I have like fast computation times. So these are two like challenges in like state estimation for continuum robots. And this is what I want to talk about today. Specifically, I want to talk about like a method I recently worked on using Gaussian process regression on SE3 for continuum robot state estimation. So the general workflow kind of like of state estimation, just like on a very high level, can be kind of broken down in like 3 parts, very simplified. So usually we start with a prior distribution of possible robot states. So I have like some prior model that gives me a probability distribution of the states that my robot can adhere to. And I have like some mean, which is usually the most likely state of this distribution. And then I have a covariance matrix that describes kind of the uncertainty or like the range of this distribution. And I can like draw random samples from this distribution, and it leads to something like depicted here. So this example is like a prior distribution where the mean of this distribution is just a straight continuum robot, and I have like different samples drawn from this distribution. And the idea is then to use additional sensor information of my robot. So for example, I can measure, let's say, poses along the length of the robot or other matrices. And then I want to fuse this sensor information with my prior distribution to result with a posterior distribution that now gives me a new probability distribution of robot states that incorporates these sensor measurements, again, giving me a mean for the most likely robot state that would match these sensor measurements, and then some covariance matrix that expresses the uncertainty of this measurement. So these are the main 3 steps of state estimation, and we will go into each of these in a bit more detail in the following. But before we do that, I actually want to talk about some very interesting kind of analogy. There's actually a very nice analogy between continuum robots and mobile robots. So if we look back to just look very briefly how we actually model the shape of a continuum robot, we have the center line that is parameterized along the arc length S. For every point along this arc length S, I can describe pose and my state variables to describe its shape. Now, if we look into mobile robots, here on the left, it's just like one very typical mobile robot depicted. It's the Mars rover. We look at the way we mathematically describe their motion. We usually do this with their trajectories. And the trajectories are defined as like a sequence of poses along a specific time frame. So along my time t, starting at time t0, going to like the endpoint of my trajectory, a robot could like follow this curve in 3D space, where like every point, at every time point along this trajectory, I can define the state of my mobile robot with a pose and with its velocity. And now, like looking at these 2 equations, the way we describe the shape of a continuum robot in like a differential form is like almost equivalent to how we describe the motion of a mobile robot in like differential form with respect to its trajectory. We kind of exchange our continuous parameter arc length to the continuous parameter time, and then my strain becomes my velocity, but the equations are very similar. And this is actually where like this work kind of originated from. So this work was a collaboration between our lab, the Continuum Robotics Lab, and then the Autonomous Space Robotics Lab. Specifically, we collaborated with Tim Barfoot, who is an expert in state estimation for mobile robots. So in this work, we then worked together to try to repurpose some of the state estimation method that Tim developed for mobile robots to estimate the state and shape of continuum robots. So yeah, just some background. This is how this like work kind of came to be. Yeah, so going back to the method itself, these are the 3 parts of our kind of like state estimation process that we want to discuss in the following. So first, I want to talk about how do we obtain a good prior model that gives us a distribution of possible robot states. So going back to the modeling equations that we derived, just like the recap, we again have like our modeling or like our state expressed here in this differential form. And these are our modeling equations. And in state estimation, now the idea is to kind of like inject or corrupt these modeling equations with some process noise, which then that kind of represents the inaccuracies or the uncertainties that my like prior model has. So one main idea would be to add some process noise to this term here for the differential equations for my strain variables, and like inject my noise here. But we will actually take a quite extreme standpoint here and like replace the whole right-hand side of this equations with process noise. And in this specific case, the process noise is a Gaussian process with a zero mean Gaussian and then some associated covariance matrix. So this, again, this might seem quite extreme because I kind of like throw away my modeling knowledge and just replacing it completely by noise. But we will see, like in the following, that this actually results in a very efficient and elegant mathematical formulation that leads to a nice system that we can solve in terms of our state estimation. It's kind of like one benefit. And the second benefit is I make like very little assumptions about my prior model, which later leads to the fact that we can apply the state estimation approach to any type of continuum robot as long as we have enough sensors kind of like attached to it. So now these are my new modeling equations corrupted with some process noise. And the idea now, so this is the derivative of my state with respect to the arc length. The idea now is to stochastically integrate these equations to obtain an expression for my state x of s. And then ideally, or consequentially, this state will again be a Gaussian process with some mean and covariance associated with it. So in this picture, then we will get like a distribution where the mean is the most likely state of my continuum robot, where we have like some uncertainty expressed by the covariance here expressed in gray. The main problem now is that integrating these equations I show here is actually not that simple, because we're actually working with Lie groups here. So we have like non-linearities in our equations, and it's like really difficult to like integrate them in like a nice like closed form way. And that's kind of what we want in terms of like an efficient formulation of our state estimation problem. So to solve this problem, there are kind of like two things that we do. So the first thing is we, instead of considering the whole center line of my continuum robot continuously, I like discretize the state at certain points k into like different nodes, like estimation nodes. So it's like one thing that I do. And the second thing is I do that I kind of like between two individual nodes, I define local variables to express the pose. And these local variables are defined in the Lie algebra. So while our kind of like global variables are defined in the Lie group, we have local variables here that are defined in the Lie algebra, which is the tangent space of Lie groups. And the main advantage is that in the Lie algebra, I can do all the normally like math operations that I can do with Lie group that easily. I can like subtract values, I can differentiate values, I can like interpolate in Lie algebra. And that's all stuff I can do in the Lie group because of all the constraints I have to work with, mostly arising from the constraints of the rotation matrix in my Lie group. And once I have like my local variables here defined in Lie algebra between two nodes, and I can easily transform between Lie group and Lie algebra using the matrix logarithm and the matrix exponential. So I don't want to go too deep into Lie groups and Lie algebra here, so I will like leave it with that. But we're now just following the same approach. Now using our local variables, I again inject some like process noise in my equations. So here I inject the same zero mean Gaussian on the second derivative of my local variable. And I can now rewrite my differential equations as like ordinary differential equations that are in fact linear. So I have my local pose variable and the derivative of my local pose variable as my Markovian state. And now this expression I can actually integrate stochastically in closed form to give me my Gaussian process prior. So we have now our prior with respect to our state, which is local, with a mean function and covariance function. And in the following, we will solve our state estimation on this local prior, and then afterwards we can, with like the usual operations, we can like transform it back into our global variables in the Lie group. All right, and so this is the development of the prior in the local form, and that results in the following prior distribution. Because we assumed a zero mean for my Gaussian process, the mean or the most likely state of the continuum robot initially will be a straight rod with like all these different samples possible, like drawn from this probability distribution. So having derived our prior, the next step is to incorporate like measurements about states of my continuum robot. So in continuum robot, we have a couple possibilities to sense the state. So generally, it's quite difficult to integrate sensors into continuum robots. So some of the main challenges are that I often cannot really use external sensors like cameras to get readings of the shape of my robot, because in all the application areas, we always argue continuum robots are like somewhere deep within some environment that's highly cluttered. So I cannot guarantee like line of sight with cameras. So I somehow need to get sensors inside of the continuum robot. Because of their small size, this can be very challenging, and I'm quite limited in terms of the options that I have. But there are some options out there, and I will talk about two that we like considered specifically. So the first one is using electromagnetic tracking coils to measure discrete poses of the continuum robot along its length. So the idea is that I have some field generator that generates an electromagnetic field that changes over time. And then I have some passive coils here in which this magnetic field will induce a current. And by measuring the current and how this current changes over time, can I kind of compute how these coils are positioned and oriented with respect to this field generator. And these coils are really small, so I can integrate them in my continuum robot body. And in this example, two of these tracking coils are placed on two different points along its center line to get two discrete pose measurements. So that's like one sensing technique that's very common. And the other one is using fiber Bragg gratings to get strain measurements. So fiber Bragg gratings, this measurement technique envisions, or in this technique, usually multiple optical fibers are integrated in my continuum robot. And then a light is kind of like, you shoot like a light through these fibers. And at discrete positions along this fiber, I have a Bragg grating that reflects a certain wavelength and transmits a certain wavelength of the light I shoot through there. And whenever this material bends off this robot, the wavelength that is reflected by each of those fibers changes, and it changes deterministically. So you can kind of, by measuring the light that is reflected through these fibers, from these gratings and through these fibers, I can compute how much the material of the continuum robot is bent, elongated, or twisted. So I can essentially obtain strain measurements of the continuum robot. And these are the two kind of like sensing techniques that we consider. And this allows us to then get measurements of both the pose and the strain, expressed as like a Gaussian, where like my measurement is kind of like the mean, and then I have like some sensor noise or sensor uncertainty expressed as like a covariance of this Gaussian. So we have like some measurements in terms of my pose and for my strain. And now, in the last step, I want to use these measurements to reside in a posterior distribution of reciting states that my robot can adhere to. And we do this via an optimization problem. So first, I just want to introduce the idea of a factor graph to like describe my continuum robot state. So what we can see here is we can see the center line of the continuum robots, and all these coordinate frames here are our discrete nodes that describe a discrete pose and strain at the center line. And now I can associate like some cost terms between each consecutive pair of poses that reside from our prior. So if you remember, our prior was derived from a Gaussian rod model, which kind of like assumes that the center line changes smooth along its length. So between two poses, I can introduce a cost term that tells me how close this center line is to the prior. So if you remember our prior, the mean was like a straight rod, just based on the assumptions that we did. And the cost term between two of these poses can tell me the cost associated from any center line to this prior. And we can do the same with measurements. So again, we have like our factor graph here. In between the poses, we have our prior cost terms. And then I can, for example, sense strain variables for specific discrete estimation nodes of my robot state. And I can also sense, let's say, the pose of specific terms. And then I can come up with like cost terms that just tell me what's the difference essentially between the current state of my continuum robot and the sensed metric from my sensor. And I can sum up all these cost terms and weight them using, for the prior, the covariance matrix of my prior, or for my measurements, I weight them with like just the uncertainty of my sensor. So I have like all these cost terms that describe how kind of far away my current state is from the prior and how well it matches the measurements. And these are all squared error terms. So like I have my error term E here, and then it's weighted by either Q, and R. And now the idea is to like add up all these costs and find like a minimum of this overall cost function, which then will be the mean of my new posterior distribution of robot states. So we can like set up our problem as a batch problem. So we have this cost function J, which like consists of these prior terms now and the measurement terms. And we want to find our most likely robot state X that minimizes these costs, where X is like just all of my robot states along the arc length going from the root to the tip, stacked in one vector as like a batch problem. So the idea now is that we solve like this our minimization or optimization problem iteratively using Gauss-Newton. So we, in every point, we linearize this cost function about an operating point with respect to X. So that will result in a structure looking something like this. It's not too important to understand the linearization or like this equation, but what's cool about this is that when we now solve the linear system, we actually get a system matrix that is block tridiagonal in every step of our Gauss-Newton algorithm. I just wanted to highlight the sparsity of this block tridiagonal matrix. So this is the matrix that we solve in every step of our state estimator. So it's highly sparse, which makes the state estimation problem very efficient. I just want to provide some kind of like understanding of what we are seeing here, because we're dealing with squared error terms. You can like think about it that way, that like like along the two dimensions of my matrix, I kind of like move along my robot length. So on the top left corner of my matrix, it's like robot length 0. And this here is the kind of like end point of my robot center line. And then each of these kind of blocks is one estimation node of my robot in this like stacked batch problem. And we can see that like this matrix has fill-ins at like very specific points. So we can see that every node is only connected with like neighboring nodes, which comes from the prior, because like this node is not like associated with like any other node except like its neighboring node, which leads to this block tridiagonal form. And additionally, the measurements of specific robot states are just like on the block diagonal itself. So in this example, we have two discrete pose measurements for like the middle, like at half of the length of my robot and at the tip of the robot. And these only lead to fill-ins directly on this diagonal. So in any case, this system matrix is highly sparse, which allows me to actually solve this problem linearly with respect to the number of discrete nodes that I choose along my robot arc length. As like one of the main kind of like advantages of this methods is like how efficient it is. So after this optimization, I obtain my most likely robot state, which is the mean of the resulting posterior distribution. And I can also extract or compute then the uncertainties of each of those nodes along the arc length. And another very nice feature of the state estimation problem is that, or the state estimation method is that can only estimate my state at very sparse discrete nodes, and then afterwards use Lie algebra to interpolate between these nodes to get intermediate states and also intermediate uncertainties. So I want to talk about some results in terms of how we evaluated these methods. So we considered a real robot setup with a tendon-driven continuum robot, shown here, where we have 2 pose measurements. And we took some ground truth measurements by just scanning a point cloud of this robot, which then gives us a series of ground truth frames and 2 sensor frames that are used in our state estimator. So the state estimation method not only has knowledge about 2 specific points of the robot, but will give us an estimate of the whole robot shape. And you can see that this estimation is actually quite accurate with respect to ground truth, where here in the 3D shapes, the shapes almost overlap. And even here on the detailed plots where you can see the position over arc length with respect to its X, Y, and Z components also matches the ground truth very accurately, actually. And so these are some static pictures, but I think it's always cool to show some videos. So I just want to emphasize that the state estimation problem can be solved actually really fast. So here's one example where we have a tendon-driven continuum robot where we measure 3 positions equally distributed along the arc length. And then our state estimator on the left time runs in real time using these 3 discrete positions to give us an estimate of the whole center line of the robot. So I only visualize the mean of my resulting posterior distribution here, but we do get all the uncertainties in terms of covariance matrices for every estimation node along the robot as well. Yeah, you can see that it's quite fast and works kind of in real time, which is really exciting because it's often not the case if you look at other methods that do state estimation on continuum robots. And I want to talk about one last thing that we started working on as well. So we started to—
Sven, do you want questions now or later?
I'm almost done. It's only two more slides, so maybe we can defer just because I'm almost done. Okay, perfect. So one recent thing we looked into is to apply this method to parallel continuum robots. So these robots are featuring multiple individual continuum robots that are coupled together in this parallel structure, and it's envisioned that they kind of work together to fulfill specific tasks. If you're interested in that, I actually gave a talk on these structures in the my last talk here at the AI and robotics seminar. So if you want to know more about that, you can check this out. Now the idea is that we have coupled continuum robots that might be coupled to some common antifactor with some connections, and we want to get the state estimation for each of those coupled continuum robots in terms of its mean and its uncertainty. You can do this by just introducing more cost terms into our optimization. I don't want to go into too much details, but I want to show maybe one video of where we have one pose measurement of the antifactor, and by moving this antifactor out, I can compute what is the most likely state of these continuum robots, given that I know the pose of this antifactor with some uncertainty. And you can kind of model all kinds of interesting structures with that. So here you can see 2 continuum robots where I have a pose measurement of one robot, and I know that the second robot is coupled to this robot here. Or here we can even see 3 robots with different coupling information leading to these state estimation results. And in terms of outlook, so what I think would be interesting to look at in terms of the state estimation method in the future. So right now we only estimate the state of the continuum robot in terms of its shape and strain variables, but it would be interesting to, if we have enough sensor information, to maybe even estimate what is the external force that acts on the robot that led to this deformation, or maybe we can add in some additional sensing to also estimate something about the environment that this robot is moving in. And then another interesting direction would be to actually use the status estimation in like closed loop control, because as you can see in specific scenarios, this status estimation code can run in real time. So it would be cool to just see its application in like a closed loop control scenario. Yeah, with that, I'm at the end of my talk. So thanks everyone for listening. And I also want to say thank you to my lab, the Continuum Robotics Lab, and particularly to my supervisor, Jessica Bogner-Kars. And at this point, also thanks again to Tim Barfoot from the Autonomous Space and Robotics Laboratory, with whom like this work just, with whom we collaborated for this work. All right, thanks everyone. And I'm open to discuss and happy to answer any questions.
So
Yeah, thanks so much.
Again. So is there any question from Zoom?
Yeah, Sven, I have a question. So how do you evaluate like the quality of your state estimator?
Yeah, that's a good question.
Like on the technical side, like what is the best way to obtain like ground truth? What did you use? I might have missed that part.
No, it's fine. I think I went over this pretty fast because I was realizing I was already quite into my time. So the main idea is that we don't use like the sensors, obviously, that our state estimator uses for its estimation as ground truth. We use like a secondary, like another measuring technique. And usually what you want to do is you want to use like some sensing technique that is like quite accurate. So in our case, we are using a point cloud of the robot. So it's not shown here, but we have this measurement arm that is like a passive robotic arm with a laser scanner attached, and you can move that around in like 3D space. And through the kinematics of the arm, it can compute where the point cloud, like the laser scanner takes a point cloud, and then you can like attach multiple point clouds into this resulting structure of the robot. And then we like from this point cloud just got the center line, like reconstruct the center line as ground truth together with like the pose. And this laser scanner is quite accurate, so we use this as our ground truth so to evaluate the quality of the state estimator. Does that answer your question?
Yeah,
okay.
Very cool. And of course, in practice, you cannot use it because you want the robot to be inside something or someone, if it's a medical robot.
That's right. So this is just to evaluate how accurate the state estimator is, and then hopefully in like a application use case, you like already have evaluated the accuracy, and you kind of need to rely on then the uncertainty. But maybe one word to like the accuracy of the state estimator. Obviously, it really depends on the noise that you have on your sensor. If you have sensors that are like really accurate, of course your state estimator will also probably be more accurate. So it's like very, very linked with respect to that.
Mm. And okay, never mind. I think that's actually what you just answered. One more thing I wanted to ask.
Yeah.
What about these? There are these sensors that are like tubes, but that like bendable tubes that like, are they called fiber optical sensors or something like that? Have you guys considered using those?
So yeah, actually, in this example, we just bought one. We actually just bought one in October. So here we have a fiber break grading sensor going through the robot, and it gives us, theoretically, it gives us strain, but like the software that comes with the sensor already gives like some reconstructed center lines. So for like an initial test, I just from the center line used like a couple of discrete points to feed it into my state estimator to see how it works with like limited sensor information. So yeah, we're working, as I said, we're working on this like follow-up paper for these parallel structures. And we also want to use this new sensor within that paper to like evaluate it with more like, there are different scenarios of available sensor information. So it's definitely something we are looking into.
How does this new sensor work? Does it give you information at like also at discrete points or?
Yeah, so if I go back to here. So the way that works, these like fiber break gratings, they have discrete, like along the lengths, they have like discrete kind of gratings at which the light is like reflected. So at every of these discrete points, you get like a measurement of like strain or position if the software already does some reconstruction. So yeah, in this case, I don't know how much, I think we would have gotten up to 20 or 30 measurements. But for this example, I was just interested how well does the state estimator perform if I only give him 3, just to see like, yeah, how well it can reconstruct the whole shape based on like limited sensor information.
Yeah, makes sense.
Yeah, these were great questions. Thanks.
Hey, Sven.
Hi. Oh, sorry. Go
Sorry.
ahead.
Yeah, just curious. What is the price or the cost of building this entire system? Like, has this been commercialized, or like, is it very hard to build this prototype robots?
So like the sensing systems are both commercialized. I think, well, let me think, how much did we pay for the one on the right now? We just bought it, maybe like a total, maybe 60 to 80K Canadian, because you need to buy like the interrogator and like like a couple of sensors, and obviously they also charge you for the software and stuff. So yeah, I think that was definitely like one bigger purchase for the lab. And then the robots themselves, I mean, we built them all in-house, and like generally like what we do, we buy the material for the backbone. So in our case, we often use nickel titanium alloy. It's like very flexible. And then the rest of the robot, we like 3D print and route the tenons ourselves. So the prototype is it's like, yeah, it's a research prototype. So it's like just like built in the lab. But the problem often is continuum robots are not like commercially available. There's no like unified prototype. So it's often very hard comparing different methods from different labs in continuum robotics, because yeah, you don't know the hardware that they run it on and stuff like this. So that's definitely like a problem, that there's not like an off-the-shelf solution. Every lab has their own built prototype, and it's hard to compare anything sometimes. Yeah.
I see. Yeah, that makes sense. Thanks.
Do we have time for one more question?
Yeah, of course. Yeah.
Okay. Hi, Sven. Very nice talk. Very cool work. I'm just curious what your thoughts are on temporal consistency. I don't know if I might have missed it in the presentation, but did you ever consider, like, you have the time kind of this parallel between time and space? Can you also add time back into the picture, or is that not really necessary?
So yeah, right now we only consider static configurations at a time. So in our mathematical formulation, the time variable is just not there. And like in a video like this, what we do is just we consider a sequence of like quasi-static configurations and kind of map them together. And so there's no, in terms of time, there's no mathematical description of the dynamics of the continuum robot. And I think for the scenarios that we study, in which we say, okay, we have like sensor update rates fast enough, I guess, then like I think it's okay. But I think it would be really interesting to model the dynamics as well, because if you're lacking sensor information for, let's say, a couple of seconds, it would be cool to have the dynamics in there to like model how the robot would behave based on that. You haven't really thought about this, how I would like modify the methods to do that, but I think it would be generally like worthwhile. Again, like right now we don't. Yeah, sorry, go ahead.
That makes sense. Yeah, it might explode in complexity, but like having a continuous time and continuous space would be kind of cool. But
yeah, I agree. Yeah. It would be super cool. Yeah, right now what we do is like we just solve this iteratively, and then we always use the last known state as an initial guess, so we can speed up the state estimator quite a bit. So even without having temporal information. But yeah, I agree, that would be super cool. Not sure if that will happen throughout my PhD, but
yeah, makes sense. Thanks.
Yeah, I think that's a great question.
So is there any question from them?
I have one question about the method. So if I understand correctly, the Gaussian process here is defined on the Lie algebra, right?
Yes,
the local Lie algebras at every step. So if you have a measurement that's global, wouldn't you have to integrate up to that point still, or how do you handle?
Yeah, that's a good question. So like we have these discrete nodes, and then we define like generally we actually define multiple Gaussian processes that are stitched together between like like they're defined between two discrete nodes, and then between all the nodes, we like just like stitch it together. And so we are kind of limited in a way that we can, like we have our discretization norm beforehand, and then we can only take pose measurements at these discrete poses actually. So if we would have a pose measurement here in between, we would need to beforehand set up our state estimation in a way that we do include a discrete node there, if that makes sense.
Oh, I see. Right. But when you have the block tridiagonal structure.
Yes.
Oh, so you discretize between two nodes.
Yeah, so the system itself now, this one only includes the discrete nodes. Like everything in between is like not estimated, but we can interpolate afterwards, but it's not estimated explicitly. Yeah.
But to like satisfy our measurements, would you still need to like imagine comparing, you have a global measurement of the position, the cost function would look like integrate the nodes, like the deviation at every node, and then compare against the global measurement, or?
Yeah, we can just directly, let's say I have like a pose measurement at the last node. I just need to consider the offset between this last node. Like I have like in my optimization, I always have like some current state of this node, right? So then I express the difference between like my measurement and this node as my cost term. Now in terms of having a smooth center line, actually the prior cost will take care of that. So I always have like cost terms from the prior that will force my rod to be kind of smooth. So what's interesting, I didn't really go into that detail too much, but let me go back. So when we replace, so generally what I have in my strain, I have like my stiffness matrix, right? But like I replace the whole term with the zero mean Gaussian process. But the stiffness, you can kind of think about like if I have my covariance matrix here, it kind of depicts the stiffness of my material in a sense. So if I tune this correctly, I can say, changes in like shear and elongation are almost not allowed. They're like very heavily penalized in my prior cost terms, because for like a continuum robot, it doesn't really shear and elongate, but I say it can like bend and translate. So yeah, these cost terms tuning these cost terms tells me how like smooth the resulting shape will be. And I also can make sure that I have a smooth center line. Then I only need to consider measurement compared to a specific discrete node. I hope that made sense.
Yeah, okay, cool. I got it now. Yeah.
Okay,
thanks.
no, it's a great question.
I guess this is not too applicable to continuum robots, but have you considered the case where there might be discontinuities between, like imagine like there might be different stages of a continuum robot, like how to take care of this discrete transition between?
Good question. Maybe you will need to split up the problem. I don't know. And let's stitch it back together afterwards at this discontinuity. I don't know. It's nothing I really thought about it, because yeah, generally it doesn't really occur. Just the material forces the robot to always be in like a very smooth line generally. And like right now, our prior enforces the result to have this form as well.
Is there any more questions? Okay, so if there is no more questions, so let's thank Sven again for the inspiring talk.
Thanks for having me.